Welcome to the webinar. My name is Adam Barnes. I'm the head of product here at Advanced Navigation. Today, this webinar will be a joint webinar between Advanced Navigation, and I'm joined today by Ashley Cox. Welcome, Ashley.
Thank you.
So we'll jump straight on in. We'll do a quick introduction of Advanced Navigation and Cordel for those of you who are not familiar with our organizations, and then we'll talk a little bit about what we're going to go through today. So Ashley, what are we going to talk about in the first part?
So for the first section, we actually have two businesses. So we're going to cover off on, I guess, two different ways that we use INS systems. First one, our business covers off is UAV LiDAR, something we've been involved with for a long time. And then moving into more ground-based things where we're working in rail with our Cordel business.
Yeah, fantastic. And in the ground-based part, I think we'll be looking at high-speed ground applications, as well as being able to operate through GNSS denied reckoning type scenarios. So that's going to be really exciting. So on the next slide, just a quick introduction to Advanced Navigation for those who are not familiar. So Advanced Navigation is a global company with headquarters here in Sydney, nice and early in Sydney this morning as we come into summer. And so Advanced Navigation works across both commercial and defence applications in land, sea, air and space. And our mission is to develop solutions that perform in the most demanding conditions, where we offer the lowest swap C, size, weight, power and cost. And our aim is for our clients to be able to easily integrate our solutions into your unique applications to have the most accurate and reliable results. Ashley.
Yeah, so our business, we actually started as a drone business in 2012, and we still have a small portion of our business that's dedicated to doing aerial surveying. However, what we learned along the way was that we still needed to start making our own equipment. And so our first stop was building LiDAR for UAVs, so that we could get a better understanding of what was happening, particularly in densely vegetated areas, but also with power lines and other sort of difficult to reach environments. And so we now make a system. We're on our third generation of system that we make to fit to UAVs. And the other side of our business, Cordel, basically brings all of that technology down to the ground. So we've been working in rail for a very long time. And in the last couple of years, we've been developing technology that can be mounted to the front or the rear of trains to collect information, but also then automate the analytics process of actually understanding what's going on in a railway. So for us, time and place or position is really important for everything that we do, as we'll explain as we move through.
Wonderful, that's great. And if anyone can hear any construction noise in the background here, apologies for that. Surveying, we can control a lot of things, but building construction is not one of them, unfortunately. So just on the next slide here, just in terms of the format of the webinar today, we have Q&A, so feel free to put questions into the Q&A panel in the webinar. Shoot those questions through. I've got my screen in front of me, so we can answer those questions as we go. We also have an opportunity at the end to answer any questions that we didn't get to just as we were talking through the webinar. In terms of the format, probably a little bit different to what you're used to. Today it's more of a video podcast style, so Ashley and I will be having sort of an interview conversation style with less slides and less words, which is probably what we all need as we approach the end of this year. So don't be surprised if there's less to read on the screen and a little bit more to listen to in the webinar today. So without further ado, we'll jump into the first part here on taking UAV LiDAR to new heights. So Ashley, maybe you just start by describing, obviously aerial surveying can operate at many different altitudes, but you operate in the UAV or the drone space. Can you tell us a little bit about what we're looking at here, and just in terms of the type of vehicle that you build and operate?
Yeah, so as I mentioned, we're on our third generation of system. We don't make drones themselves, but we make systems that will fit to drones. And basically they allow our customers to get to difficult to reach places to quickly and accurately map an area. So that might be a surveyor, primarily it will be a surveyor looking to create a land survey. but it might be environmental scientists, it might be people working with, you know, power lines or agriculture, forestry, a whole range of different areas where the technology gets deployed. So we need a system that is lightweight and rugged and reliable, probably most importantly.
Right. Okay. So we might just jump into a video now that I guess will best demonstrate, you know, an example of one of the applications that that you work in. So we'll just get that up now, and then we'll take a look at that. If you could talk us a little bit through what we'll be watching here.
Sure. So this is a survey of Tomaree Headland in New South Wales, Australia. It's actually not far from where I live, and it was a job for National Parks and Wildlife Service. It looks a little bit pixelated coming through the video over the internet, but what our client needed was a very high resolution map of what was going on below the vegetation. And in steep, rugged terrain like this, and you'll see as we come around the back of this mountain at some point, there was just, it would have been very dangerous to get surveyors in to actually survey this area and understand what was happening underneath all of that vegetation. So what our system allows us to do is to fly over the top and, you know, achieve a certain altitude to be able to get returns from the ground, and then be able to feed that back so that this can be used for design. What they were looking to do here was create walkways around this headland.
Yeah, fantastic, fantastic. And we might just take a little bit more of a look at the system on the next slide here. And I think what's interesting is really just how small it is. You know, you're not operating a VTOL like a plane type. You're not operating at higher altitudes. You're really, you know, fitting everything into a really small footprint. If we just jump to the next slide, what's actually fitting inside your system here?
Yeah, so the key components, and this is our newly launched Lumos system. We've only released it about a month ago, and we're just shipping units now. And I've got one here just to give you an idea of the size. This weighs 1.6 kilos, and we can fly for over half an hour on most modern UAV systems. The key components in this is a laser scanner, obviously, but we need to combine that with location and timing. And so we need a very high quality INS system to be able to do that. But we also have this continual push on the industry to get lighter, so that we can get more flight time, we can fit on smaller, safer UAVs. And so for us, we've been looking and testing constantly different systems to be able to make that happen and do it in a reliable way. So in the past on our other systems, we've used advanced navigation spatial duals, and then we moved to the Certus Evo. And what we've moved into now is, because we've got our own ruggedized casing system, in order to save weight, we've actually moved into the OEM version of that to be able to give us what we need.
Yeah, okay. And that's what we're looking at just on the left-hand side of the screen there, is the Advanced Navigation Certus Evo product on the top left. That's the rugged version. And then below that is the OEM version that the Cordel is used to integrate into their latest solution. So obviously being able to reduce the size and the weight for a UAV application is really important there. In terms of, you mentioned position, you mentioned timing. What sort of requirements are you looking for from an INS? Is there anything else in terms of roll and pitch and heading that is important for this application?
Yeah, and when you're collecting data, you know, millions of points per second, as you're flying through the air on a drone, which is moving X, Y, and Z constantly, being able to make sense of all of those points coming back and turn it into a manageable point cloud is incredibly challenging. So the more accuracy you can get from your INS, the better you can make sense of all of those points that are coming back into your system. This is I should point out, this is a post-processed thing. This is not really something that you can do in real time. So it's a matter of essentially data logging with this system and then trying to make sense out of that. But if you haven't collected accurate information about where you are and where you're going, then that's not going to help you when you want to produce a survey grade point cloud to your clients.
Yeah, okay. So let's take a little bit of a look at that that workflow process, because that's quite interesting. So you mentioned that you're not doing everything in real time. Tell us a little bit about your workflow. Obviously, you mobilize the UAV, you fly a flight path. Sort of where does it go from there?
Yeah, so basically, once you've flown your mission, we need to get to a LiDAR point cloud, and that's our goal: get to an accurate LiDAR point cloud as quickly as possible. So basically, what our software allows us to do is to process the flight lines, each individual flight line, cut out any turning and cornering or getting to the actual survey side, cut that out really quickly, and then be able to process a post-process solution as quickly as possible with all the data that we want. Sometimes we don't want data that's too far away or too close to the system, and be able to achieve that as quickly as possible.
Right, and for that, I believe you've integrated your platform into the advanced navigation Kinematica software for post-processing, just to somewhat automate that process. Is that right? Yeah,
that's right. We're looking for the easiest, quickest way for our customers to be able to do that, and the ideal situation for us is a customer lands, uploads their data, it's processed, and by the time they get back to the office, it's ready to go. And we've been achieving that for years now. What we're moving towards now is an even faster solution where we can get through the data really quickly, 5 or 10 minutes from a half-an-hour flight, and you've got your LiDAR ready to go.
Yeah, fantastic. So you might have a little bit of a chat then about some of the challenges and limitations. You kind of touched on a few of the areas. So one of them you mentioned, collecting millions of points, very quickly. So how does the LiDAR point density kind of play into this in terms of thinking about the elevation that you can fly at, the point density that you need to get the ground resolution and so on?
Yeah, the biggest, I guess, challenge is maintaining a really high point density. I mean, one of the advantages of UAV LiDAR over, say, manned aircraft LiDAR is how many points we can get per square meter. So we need to try and achieve a very high resolution, anywhere between 200 to 500 points per square meter. But we need to do that without hitting trees and power lines and mountains and things like that. And in the past, and most systems that are on the market today, you will struggle to get a meaningful point cloud above, say, 40 or 50 meters above the ground, and terrain following all the way through. And our older systems, that's how they used to work. And we had this constant pressure from our customers: let me fly higher. I need to achieve survey grade outcome higher, so I'm not going to crash my system. And so for us, that was a high priority, is allowing the system to fly. And these new systems that we've got will fly anywhere. One of our systems goes up to 100 meters AGL. The other one goes up to 120 meters above the ground, or over 400 feet, and still achieve good point density and a survey grade accurate outcome, which for us is vitally important for our customers to fly safely and be able to do it. We're also, trying to maintain that reliability. Some of our systems have been out in the field now for 4 or 5 years. So we need reliability and ruggedness, because when surveyors are out on job sites all day, they tend to not look after equipment, even if it's incredibly expensive, when they get tired. So we need that reliability and ruggedness, as well as lightweight. And then you've got the challenge of getting to market with the lowest possible cost system you can as well.
Yeah, fantastic. And so then, I guess as you kind of get higher and higher, it kind of ups the stakes in a sense. You need a better LiDAR, better point density from that higher elevation, and then you need a better INS to go with it. You sort of mentioned at the start of the presentation that this is your 3rd generation. You've been kind of getting higher and higher. What's that meant in terms of the INS? You're using a MEMS-based technology. Understandably, a fiber optic gyroscope or sort of a different technology would not be suitable in this type of vehicle because of the increased weight of that sort of technology. Have you tell us about sort of the limitations and boundaries? Have we reached the edge of MEMS-based INS at this elevation? Is there room to go higher, or does that kind of bring in other challenges?
Yeah, obviously with every meter of elevation, we're increasing the amount of error that we're bringing into our point cloud, and therefore the amount of noise. Some customers that don't need to produce survey grade are okay with that, but with every time we try and push higher to cover more area, to fly faster potentially, we're taking more risks with, and there's more challenges that crop into the system. One of the nice things about UAV is that you should have constant access to GPS. If you're flying 100 meters above the ground and you lose GPS, then something's a little bit more seriously wrong. So being able to do that is a challenge. And at that point, once we get up to 100, 120 meters, we're starting to reach the sort of legal restrictions of what you can do with the drone in most countries. So that's a really good place to get to. The challenge there is, can we improve accuracy? And that's really only going to happen with better LiDAR systems, but better INS systems as well.
Yeah, right. It's interesting you mentioned kind of that height limit, because naturally we always think higher is better and faster is better and bigger is better. So you mentioned regulatory restrictions, and so do you kind of see like a bracketing of where UAV kind of hits a regulatory ceiling, and then both regulatory wise and vehicle type wise, you're actually getting into a whole nother, I guess, market in regards to how you actually operate the survey?
Yeah, absolutely. I think we've seen it in the production of drones, is that regulatory restrictions challenge the industry to meet certain specifications and weights and all of those sorts of things. And the same is more or less true for UAV LiDAR as well, is that now that we've hit a ceiling, we need to be able to improve on that. Although what we're achieving now is a real game changer. What we've released in the last month is a real breakthrough in terms of being able to hit these height limits within a certain budget for our customers and maintain a really nicely accurate point cloud as well.
Yeah, sure. And understandably, I guess if you start putting planes up in the sky and you need pilots, you need regulatory requirements, that's a whole different kind of application at that point, isn't it?
Absolutely.
Yeah. And have you played much in the VTOL space? Sort of, how do you see that there's potential use of a vertical takeoff and landing type autonomous aerial vehicle in this application, or does that kind of present different challenges?
Yeah, it definitely is. I think we'll be moving to that more quickly. There's still regulatory challenges in most countries flying a VTOL system, and then there's restrictions on the quality of the LiDAR systems and how they function when they're flying on essentially a plane, a lightweight plane. And so we have built systems like that. The challenge is being able to deal with speed and heights and all of those sorts of things into the future. And yes, that will require in order to get reliable, it'll require a step change in regulations and a step change in the technology to be able to improve on all of those things.
Yeah, okay. It's an interesting evolution, isn't it? It sounds like you've done a great job of sort of focusing on that space that fits in all of these kind of constraints in terms of flying below the regulatory airspace as such. We just had a question come in on the Q&A, which I think would be interesting. The question is, what is the difference in accuracy of the ground points under heavy vegetation in LiDAR collected from UAV drones that can fly lower, so such as the Lumos that you have, versus more traditional LiDAR collected by planes?
Yeah, in terms of the accuracy, everyone should be sort of aiming for a sub 50 millimeter accuracy, and that's something we've always aimed to do. We now with our system are getting under 40 mil and even under 30 mil in some cases with our system to be able to do that. So that's sort of the standard in the UAV world. There's systems that are way outside that. But the majority of them are trying to achieve that. But generally, that's what surveyors will demand out of a system. The difference between that and using a manned aircraft is that the manned aircraft is moving very, very quickly. So it's very difficult for it to not so much get the accuracy, but get the density that's required to be able to do it. They should be aiming for the same levels of accuracy. They don't always achieve it, but often it's difficult to measure that accuracy because you have far fewer points per square meter than you would get if you're just moving along with a multi-rotor UAV.
Yeah, so it sounds like in summary, you have a lot more control, and hence essentially you can actually create a more detailed point cloud when you've got, I guess, complex terrain or or vegetation. If
Absolutely,
that's
absolutely,
part of
and that's a key thing with the vegetation. It doesn't really restrict the accuracy, but what tends to happen if you don't have the right LiDAR sensor or you're going too quickly is that you won't get any points through the thick vegetation. And by using UAV LiDAR, you can throw lots and lots of points through, get multiple returns from those points, and be able to get down through the vegetation and actually hit the ground, get more ground returns, and therefore have a better understanding of what you're doing.
Yeah, fantastic, fantastic. We might kind of make our way into some of the land-based surveying now as a contrast from talking about UAVs. And so the focus here will be kind of contrasting the MEMS-based technology that you've been using for aerial surveying with that of being able to use product that's a little bit heavier, such as a fiber optic gyroscope or fog-based technology for land surveying. Can you tell us a little bit about your experiences in what you've been doing in land? And I guess maybe we can start with some testing that you've been doing on Advanced Navigation's new Boreas D90, which is a strategic grade fog gyroscope. And maybe talk us a little bit through this testing that you've done.
Yeah, absolutely. So, as I mentioned before, we work with rail. That's our key focus. But accessing rail to test things all the time is incredibly difficult. So we tend to do a lot of our testing on road to just get things out there, test it, see what it looks like, and then bring that into the rail environment once it's ready, to go, so that we're not making mistakes while we're in the rail environment. So what we're really looking for out of a fog-based system is the ability to continue surveying even if we lose GPS. We don't have the same level of access to GPS as you do on a drone for obvious reasons. And in rail, you've got additional problems. You've got trees over the railway where it might potentially be stopped. You've also got tunnels, which can be quite long, if not very long. And so being able to, extract a meaningful, what we would call a flight line, but a path out of the system is increasingly challenging. So for us, a fog-based system can get rid of some of those errors that we introduce. So our early testing of this system shows us that we can do that. We can absolutely lose GPS for periods of time and continue on and not have to worry about what's our actual trajectory at the moment. We can make a meaningful understanding of that far more easily because we've got a more accurate path.
Yeah, right. I guess one of the difficult things with testing anything in this space is really like what is your reference or source of truth. So we're looking at here a test that you've done where you've basically travelled the same road in both directions. How does that help you actually work out then the accuracy of the system?
Yeah, look, LiDAR is a great way to actually proof out INS systems, because if your INS is not performing well, you're going to get a mismatch, particularly if you drive back the other way from the way that you've come, you're going to get a mismatch in where that LiDAR sits. It becomes very, very obvious very quickly that something's wrong. And so what you're looking for is a nice clean point cloud where all the points look the same, no matter which way you're traveling. And you can see with data like this that everything's nicely matched up. There's not some huge shift in the data that would cause concern that something hasn't quite synced properly, or something hasn't gone right there. The trajectory for both is the same essentially. Yeah,
right. I mean, it's really interesting to look at sort of how you can test, the LiDAR and the INS system together, in a road-based application where you obviously it's very easy to get access to, and it's a little bit more challenging in trains. So maybe we'll talk a little bit about trains. You mentioned a couple of things before, one of them being around dead reckoning. Maybe just before we get into that, if you could tell us a little bit about, what are the unique challenges of trains, aside from being able to get the equipment on there, in terms of how they operate, the environment?
Yeah, so rail is quite a harsh environment. Systems need to live on there for years. And so ruggedness is even more important than it is in a UAV surveying space. And you're also covering huge areas effectively unmanned. So our systems are completely automated. We can't rely on staff in the rail corridor to, really care about the data that we're collecting. And so we need to automate that process completely. Every time a train starts, the whole system needs to turn on, tell us that it's scanning correctly, even though this might be, in this case, we're in the US with the system, but we're in Australia watching the actual system collecting data. So we need to be able to rely on that. Missing data is effectively missing kilometres of revenue. And so you need a super reliable system. And then you've got this added problem where you're going to lose GPS at some point, and you need to be able to show your clients that you can still understand what's going on in their rail environment. What we're trying to do is effectively automate the process of railway scanning and provide a whole range of metrics that are usually provided by doing this by hand, and automate that and give that data to our clients.
Right. And I believe these also operate at quite some speed.
Yeah.
And so is that another reason where, say a fog-based INS may be chosen over MEMS-based technology?
Absolutely. We need to be, super comfortable with speeds at this stage, up to 160 kilometers or 100 miles an hour, because that's sort of the baseline that most of our customers require for the environments that we're in at the moment. That's only going to get faster. You start looking at something like a bullet train and, or a maglev, and all of a sudden the speeds increase hugely. So you need to still be able to cope in those environments into the future to deliver something reliable.
Right. We've got a video here, I guess, to sort of help illustrate what you're describing here. We'll just get that playing, and then maybe you can describe to us, sort of the practical elements here.
Yeah, this is a really good example of how important position is. I mean, effectively, we've almost got a Google Maps for rail, in that we can click anywhere on a map, and then we can see what's going on in those areas. And what we do is sort of automate the ticketing process to say something's not within spec that we're looking for. So here we're going through the rail corridor. You can see the two track center lines, and we can measure those very, very accurately, which is important. But we can also measure the clearance, because we've got this trajectory through the middle of effectively the rail. We can automate the trajectory of it, and then see with the LiDAR if there's any clashes that are outside the requirements of the client. So if there's vegetation, for example, that's getting too close to the train, we can flag that in both video and LiDAR and report that back to the clients with a very accurate position of where it's occurring. And it's not just for vegetation, it's for all sorts of things that could create problems in the railway, the ballast that's sitting underneath, other potential objects as we're passing through the corridor. So being able to rely on the position of the data that we're collecting is the most important thing that we do.
Yeah, right. And you can imagine, as soon as you go into a tunnel, being able to do dead reckoning to maintain a sense of position is really important.
Absolutely.
To put that solution together.
Yeah,
fantastic. I think that kind of brings us to the end of the second part. So we'll just sort of recap. We've kind of gone pretty quick this morning, or for us in Australia. So in the first part, we talked about how UAV allows us to fly, under and within regulatory requirements. It obviously varies by country, but really is kind of what makes this application really interesting is kind of a defined ceiling, but also then being able to fit a payload within a UAV. Again, there's certain regulatory requirements in some countries about the size of the UAV, the weight of the UAV. And so then being able to get such a high density point cloud that is accurate, being able to fly, up to 120 meters at the moment is really fantastic. We're talking size, talking weight, making it cost effective within this application space is really exciting. And really, I think, what I can see, Ashley, is that your application really allows customers to really minimize their operational costs, have fast access to being able to conduct a survey. There's limited red tape, shall we say, in terms of getting out and doing a survey, and then just going through the workflow and getting that that data back in the hands of the customer very quickly is so important. And I know you've also been doing work for fire services and various agencies like that, where, you know, certainly with things like climate change, being able to being able to get out in the field and collect data that might affect planning or how we deal with natural disasters as well as, another interesting application that that can be done as well. And so I guess that kind of looks at this the MEMS-based INS space in terms of those limitations, and that's something that Advanced Navigation are very proud of, is really pushing those limits in MEMS-based INS to. We talk about near fog technology. Of course, we then push fog technologies as well. So you kind of see MEMS pushing into the fog space, and then fog pushing, really up into that strategic grade, precision. And so that sort of takes us into the second part, where we talked about land-based surveying, the challenges there being speed and GNSS denied or patchy GNSS, such as going into tunnels or dense tree canopies. So being able to have an INS that can provide that continuous position and attitude data, even at high speeds, with vibration, a lot of movement, and then going into tunnels where we don't have GNSS, is really interesting to look at how you can kind of put the technologies and package them together. And as you mentioned, to make that automatic, really, so that your customer can, basically run the train and not have to think about doing surveying at the same time. It's really great to see that all come together.
Yeah, absolutely.
Try to add there, Ash, in terms of a recap?
Yeah, I guess just to tie that all off, our goal really is to make it easier and a lower cost to collect this data, so that you can get it more often. If you can get the data more often, that's going to help you make more decisions and better decisions, and more quickly, and see trends that are happening over time. Yeah,
fantastic. Well, we do have a few minutes for Q&A. So if anybody has any questions, feel free to drop them into the Q&A. We'll just sort of wait a minute to see questions coming through, and then we'll look to wrap up the webinar.
Adam, I'm just putting my email address into the chat. If anyone would like to reach out and discuss more about how we're using these products, very happy to discuss further.
Yeah, fantastic. Yeah, so Ashley Cox is the COO and founder at Cordel and Xcore. So looking at both the UAV, the Lumos system that they've got, as well as working across various land-based applications. So if you have any interest there, feel free to reach out to Ashley. And then if you're interested in reaching out to Advanced Navigation, we'll be sending out